into cot x. These are some of the very standard differentials of some very standard functions. So it is very much important for you students to remember all these differentials. Even if someone wakes you up in the night and asks you the differentials of these functions, you should be able to tell the differentials of all these functions. So please learn them by heart. Now let's look at the basic rules of differentiation. The first is d by dx of fx plus minus gx is equal to d by dx of fx plus minus d by dx of gx. That is, the differential coefficient of the sum or the difference of two functions is equal to the differential coefficient of the first function plus minus the differential coefficient of the second function. The second is d by dx of fx into gx is equal to fx into g dash x plus gx into f dash x. That is, we multiply the first function with the differential coefficient of the second function plus we multiply the second function with the differential coefficient of the first function. The third is d by dx of f by g. Now if any function is of the form of fx by gx, so the differential coefficient is equal to gx into f dash x minus g dash x into fx divided by gx whole square. That is, the differential coefficient of any function of the form f by g is equal to denominator into the differential coefficient of the numerator minus the differential coefficient of the denominator into numerator whole divided by the square of denominator. This is also called as the quotient rule. The fourth is d by dx of f of g of x. So if we have a composite function, then the differential coefficient is equal to f dash of g of x into g dash x. Now this is a very important rule and it is called as the chain rule of differentiation. Now why does this happen? Let's see the proof of this. Let us say that y is equal to f of g of x. Let z is equal to g of x. Then dz by dx would be equal to g dash x. And this would be y equal to f of z. Now dy by dz would be equal to f dash z, and that is equal to f dash of gx. Now dy by dx would be equal to dy by dz multiplied by dz by dx. Now we know that dy by dx is equal to f dash of g of x into dz by dx is equal to g dash x. Thus we see that dy by dx is equal to f dash of gx into g dash of x, and this is known as the chain rule of differentiation. Thus dy by dx is equal to f dash of gx into g dash x. Now let us solve an IIT problem. This appeared in 1978 and differentiate from the first principle sine of x square plus 1. So the function given to us is sine of x square plus 1 and we have to differentiate this function from the first principle. So fx is equal to sine of x square plus 1. Now f dash x from the first principle would be equal to limit of sine of x plus h whole square plus 1 minus sine of x square plus 1 whole divided by h, then h tends to 0. Now we know that sine of a minus sine of b is equal to 2 times cos of a plus b by 2 into sine of a minus b by 2. This is once again a basic trigonometric identity. Now we use this identity here and get the expression as 2 times cos of x square plus h square plus 2x into h plus 1 plus x square plus 1 whole divided by 2 into sine of h square plus 2x into h divided by 2. Now this is again whole divided by h and h tends to 0. Now when h tends to 0, we get f dash x equal to 2 times cos of x square plus 1 because these two terms will be equal to 0 and this would be equal to x square plus 1. Thus we get the expression as 2 times cos of x square plus 1 into the limit of this expression sine of h square by 2 plus xh whole divided by h when h tends to 0. We take the limit of this expression. For that, we multiply and divide this expression by h square by 2 plus xh, and as we know that sin x by x is equal to 1 when x tends to 0, so this expression would be equal to 1. And in this expression we take out h as common, and h gets cancelled, and when we put h equal to 0 here, we get the limit as equal to x. So the limit of this expression is equal to x, hence f dash x is equal to dy by dx, which is equal to 2 times cos of x square plus 1 into x, or equal to 2x into cos of x square plus 1. Now let's solve one more problem. Find f dash x for fx equal to cos x into ln x plus tan x divided by x, and part B is fx equal to log of sine of x square plus 1 divided by x minus 1. So in this problem we have to find f dash x. So let's try to solve the first part. Fx is equal to cos x into ln x plus tan x divided by x. Let us say that gx is equal to this expression, that is cos x into ln x. Now we use the product rule here, that is we differentiate this function with respect to x in the following way. This gets differentiated to minus sin x into this function ln x, plus we keep this function as it is cos x into, we differentiate this function and the differential coefficient is equal to 1 by x. Hence g dash x would be equal to minus sin x into ln x plus cos x into 1 by x. Now hx is equal to tan x by x. Now we use the quotient rule here, and h dash x would be equal to x into differential coefficient of this expression, that is sec square x, minus tan x into the differential coefficient of x would be equal to 1. So this gets multiplied by 1 and whole divided by x square. So f dash x would be equal to g dash x plus h dash x, or f dash x is equal to minus sin x into ln x plus cos x by x plus x times sec square x minus tan x whole divided by x. So this is the value of f dash x when fx is equal to cos x into ln x plus tan x divided by x. Let's try to solve the second part. Fx is equal to log of sine of x square plus 1 whole divided by x minus 1. So we see that this is a composite function, and we apply the chain rule here to get f dash x. Now log of x is equal to 1 by x, so this would be equal to 1 by sine of x square plus 1 divided by x minus 1 into the differential coefficient of sine x is cos x, so this gets equal to cos of x square plus 1 divided by x minus 1, and the differential coefficient of x square plus 1 divided by x minus 1 would be x minus 1 into 2x minus x square plus 1 divided by x minus 1 whole square. So as such, this expression is nothing but cot of x square plus 1 divided by x minus 1 into this expression reduces to x square minus 2x minus 1, and we have x minus 1 whole square in the denominator. So f dash x would be equal to cot of x square plus 1 divided by x minus 1 into x square minus 2x minus 1 whole divided by x minus 1 whole square. We have seen the derivatives of trigonometric functions. Now it's time for us to see the derivatives of inverse trigonometric functions. Sin inverse x has the differential coefficient of 1 by under root of 1 minus x square. Here x lies in the interval minus 1 to 1. Similarly, cos inverse x has the differential coefficient equal to minus 1 divided by under root of 1 minus x square. It is same as the differential coefficient of sin inverse x, with the exception that there is a minus sign here. Again, x lies in the interval of minus 1 to 1. If y is equal to tan inverse x, then dy by dx is equal to 1 by 1 plus x square. X belongs to the set of real numbers. Similarly, cot inverse x has a differential coefficient equal to minus 1 by 1 plus x square. Here again x is an element of real numbers. This is the same as tan inverse x, again with the exception that there is a minus sign here. The next is sec inverse x. So dy by dx is equal to 1 by mod x into under root of x square minus 1. Here mod x is greater than 1, and cosec inverse x has a differential coefficient equal to minus 1 by mod x into under root of x square minus 1. Here again mod x is greater than 1. So these are the derivatives of inverse trigonometric functions. Let's try to see how we derive at these results. Let us say that y is equal to sine inverse x. Now x would be equal to sine y. Now dx by dy would be equal to cos y. Here we differentiate x with respect to y. So dx by dy is equal to cos y. Now cos y could also be written as under root of 1 minus sine square y. So dx by dy is equal to under root of 1 minus sine square y. But sine y is equal to x. So dx by dy would be equal to under root of 1 minus x square, or dy by dx would be equal to 1 by under root of 1 minus x square. So the differential coefficient of y equal to sine inverse x is equal to 1 by under root of 1 minus x square. Similarly, we calculate for y equal to cos inverse x and so get the result as dy by dx equal to minus 1 by under root of 1 minus x square. Now let's look for y equal to tan inverse x. So x would be equal to tan y. Now dx by dy would be equal to sec square y, because the differential coefficient of tan y would be equal to sec square y. Now sec square y could be written as 1 plus tan square y, but tan y is nothing but equal to x. So dx by dy would be equal to 1 plus x square. Thus we get dy by dx equal to 1 by 1 plus x square. So similarly, we can find the derivatives for y equal to cot inverse x, sec inverse x and cosec inverse x. So based on the differentials of inverse functions, let's try to solve an example. Find f dash x for fx equal to tan inverse of under root of 1 plus x minus under root of 1 minus x whole divided by under root of 1 plus x plus under root of 1 minus x. So in this problem, we have to find f dash x for fx equal to this expression. Now given that y equal to fx equal to tan inverse of under root of 1 plus x minus under root of 1 minus x whole divided by under root of 1 plus x plus under root of 1 minus x. So let's try to substitute x equal to cos 2 theta. Now 2 theta would be equal to cos inverse x. So 2 theta should be in the range of 0 to pi, or theta should be in the range of 0 to pi by 2. Now we also know that 1 plus cos 2 theta is equal to 1 plus 2 cos square theta minus 1. 1 and 1 gets cancelled and what we get is 2 cos square theta. Similarly, 1 minus cos 2 theta is equal to 1 minus 1 plus 2 sin square theta, which is equal to 2 sin square theta. Substitute the value of x in fx, we get y equal to tan inverse of modulus of root 2 cos theta minus modulus of root 2 sin theta whole divided by modulus of root 2 cos theta plus modulus of root 2 sin theta. Now root 2 gets cancelled and what we get is y equal to tan inverse of mod of cos theta minus mod of sin theta whole divided by modulus of cos theta plus modulus of sin theta. We divide numerator by cos theta and denominator by cos theta. So sin theta by cos theta is equal to tan theta. Thus y is equal to tan inverse of 1 minus modulus of tan theta whole divided by 1 plus modulus of tan theta. Now as we see that theta lies in the interval 0 to pi by 2. Therefore tan theta lies in the first quadrant and so tan theta is positive. So modulus of tan theta would be equal to tan theta. Thus y equal to tan inverse of 1 minus tan theta divided by 1 plus tan theta. Now 1 minus tan theta divided by 1 plus tan theta could be written as tan of pi by 4 minus theta. So y is equal to tan inverse of tan pi by 4 minus theta. And as theta lies between 0 to pi by 2, therefore y is equal to pi by 4 minus theta. Thus y is equal to pi by 4 minus, we put the value of theta